Hi, this is Dr. Viv. We will soon be studying integration in some detail. When you integrate, you have to be concerned about the path you take to integrate, because a vector field and a scalar field exist throughout R3. So if you're going from some initial point I to some final point F, you also need to specify the path taken from I to F. Or if you're integrating over a surface, such as you're integrating this thing, or a double integral over the surface, then you have to also talk about how the surface may be oriented, if it's got an outward normal or an inward normal. So the normal vector has to be specified in that case. So these are the topics where you have to worry about what kind of path you're looking at, if it's a continuous path or if it's a jagged looking path like a staircase. And here you have to worry about if the surface in question is orientable like a sphere or not orientable like a Mobius strip or a Klein bottle. So the subject that deals with these things is called topology in mathematics. We don't need much topology at all, but we just need a little bit to understand the setup. So first of all, let's define properly what a path is. In lower level courses, you just believed that a path was a straight line or some wavy line. Is there a precise way of defining what a path is? It turns out there is. A path is a map, gamma, that takes any interval of the real line, including the entire real line if necessary, into R3. So an example of this would be if I take, I can write the following. I can write it as cosine t, comma sine t, comma t. So what I've basically done is I've taken the parameter t and mapped it to cosine t sine t t. Now if you look at what this might be, it's actually a helix. Cosine t sine t, that's a circle. And then I have a t, so it's going to lift the circle out of the xy plane and continue on its way along the z-axis. So that's a helical spring, maybe. So this is a fun way to describe different paths. And when we do this, it's called the parametrization of the path. And the parameter is located here. And of course, the coordinates of the point that of the path that you're parametrizing occur on the other side. Now, surfaces are exactly like that, except that you'll have two variables now. So sigma, you go from R2. It's a map from R2 to R3. Now, a great example of this would be the map that embeds the spherical surface into R3. So let's take a unit sphere. So I'll take the angle theta, I'll take the angle phi, and I'll embed it as follows. For the x coordinate, I have sine theta, cosine phi. For the y coordinate, I have sine theta, sine phi. And for the z coordinate, I have cosine phi. So this actually describes the embedding of a two-dimensional patch. I'm taking theta and phi, of course, it's not going to be the entire R2. Theta is only going to wander from negative pi to pi, okay, negative pi to pi, and then phi is going to basically go from 0 to 2 pi, where 2 pi and 0 are considered the same, so I'll put that as a half open interval, and that'll pretty much give you the embedding of the sphere. I don't want to draw a sphere. It'll look just like a circle if I do it, but if I tried, this is how it would look. That's x, y, z, and then if I draw a pretend sphere, then okay, I'll do this shading to make it more believable. This coordinate here is actually where your theta ends up, and phi is the projection like that. So that's where your phi ends up. So that's a good way to describe a circle, a sphere. And other embeddings, of course, there are as many embeddings as you can think of functions. I use the word embedding, and that's also an embedding, by the way. I've taken a interval of the real line and made it into a helix. I've taken a portion of the two-dimensional plane and shaped it into a sphere. So these are called embeddings. Okay, now let's look at the important operator known as the boundary operator next. What does the boundary operator do? Well, it tells you what the boundary of something is. So let's take a simple example. Suppose I don't have a sphere, but only a hemisphere or half a sphere. So what is the big difference between a full sphere and a half a sphere? One is you can put water into the full sphere and shake it around and no water will spill. If you try that with a bowl, of course, water is going to spill. And that's pretty much the main difference. If we call this the surface sigma, then that's called the boundary of the surface, del sigma. Do not confuse this del with the partial derivative. So the del is called the boundary operator. And its only purpose in life is to take the surface you have and declare its boundary. It takes your surface to a dimension that's lower than that. So the boundary operator takes you from a space of n dimensions to a space of n minus 1 dimensions. In this case, the boundary applied to a two-dimensional surface, which is a disk. Now, you may not believe that a hemisphere is a disk, but topologically speaking it is. What you do is you start squishing the other part of the hemispherical part and make it into a disk. So the two things are the same. Okay, the squiggly sign is sometimes called homeomorphic. Homeomorphic means they have the same shape. You may have heard these things when you studied or when you read some popular science books, that a coffee cup is the same. Well, this one has tea in it, but not coffee. A coffee cup is the same as a donut. Well, the reason for that is because you have this handle, and the handle creates the scope for a hole. Let's try to transform the coffee cup into a handle, into a donut. Here's how it works. You take this coffee cup. I'll draw it a little more simply than my fancy cup. Okay, and then what you do is you realize that this part can simply be replaced by a point. So now you just have the handle, and that's the donut. So that's how the coffee cup equals donut happens. And we again put that squiggly sign. So once you have the boundary operator, you can do some interesting things. And one thing you can do is to define the orientation of a surface. So what we're going to do is we'll do that. Let's take some surface. It's just lying out there like a floppy hat. And we want to define what it means for this floppy hat to be oriented. Well, so what I can do is I can take a curve that lies on this floppy hat, a closed curve, okay, and then I can thicken it a little bit. This is called a collar thickening in differential topology. So you thicken it by a collar thickening, okay, and that collar thickening will produce the ability for you to define what's called a smooth normal vector field. And this normal vector field will point either outside or inside. Now, as you go around the entire surface, if that normal vector field comes back to itself, if you go around 2 pi and it comes back to itself, then the surface is orientable. If it gets flipped, then the surface is non-orientable. A classic example is the Mobius strip, which is got by taking a strip of paper and twisting it before you join it up. So that's how the Mobius strip would look. So what happens in this case? Let's look. I haven't, this almost looks like a collar, so I won't bother doing the collar thickening construction. You take the normal vector field here, n hat, and let's see what happens to it. It starts, it starts going inside. So that is pointing there now. And now it's going to go here, it's going to go here, and then it comes exactly opposite to itself, minus n hat. And then you have to go around once more to get back to where it is. Now, by the way, that's a characteristic of things called spin half particles in particle physics. An electron takes 720 degrees to come back to itself, and that's why it's called a spin half particle. So these are really interesting things, I feel. And so the orientability of a space is it's a very important fact in our theorems that are going to be discussed for the rest of this week. The proper definition of a normal vector, if you're really interested, is first you put a function phi on this surface, and then the normal vector is defined as the gradient of that scalar function divided by the magnitude of that gradient. If you've taken multivariable calculus and you have to do the normal vector, then you do that. And here phi equals 0 is considered the surface. Because remember, phi is a function of x, y, z. It describes a vector field on the entire space. So you have to set it equal to something in order to form the equipotential, or in this case, the surface. So these are some of the different things I thought I should talk about before I launch into the famous theorems. There are two important theorems, and they're called the divergence theorem of Gauss, and the other one is called Stokes' theorem. The divergence theorem says something interesting. It says the flux of a vector field, which is going to be defined later, but I'll write it here, and I'll describe these symbols later on. That's the flux of a vector field. Is equal to the divergence over the volume of that vector field. And here the surface is the boundary of the volume. And that arrow sign means that it's oriented. That's Gauss's divergence theorem. Stokes' theorem says the following. A certain quantity called the circulation, circ, which is defined as the closed integral over a line curve of the vector field dotted with dr, is going to be the double integral over an open surface of the curl of that vector field dotted with some area element, which I'll call d sigma, and this one is over a surface S, and the stipulation here is that the curve be the boundary of that surface, and that also is an oriented line integral. So you can see how these topological ideas show up. You need the curve to be oriented, and you need the surface to be oriented, and you need the curve to be the boundary of the surface here, and the surface to be the boundary of the volume here. Let me tell you an important instance in the history of physics where not following the topological rules led to trouble, and the poor person who paid for that was the French physicist Ampere. Ampere's law is a very famous law in electricity and magnetism. If you've taken a beginning course in university physics, the second part of that course will deal with Ampere's law. Well, what do you know? Ampere goofed up. He did not consider topology, and so his law is wrong. Later on, Maxwell came and considered topology properly and introduced what's called now the famous displacement current of Maxwell, and that was required to be added to make his statement topologically meaningful. So because Ampere did not consider all these seemingly fancy and wishy-washy things, but they're actually very important, and it changes the very nature of reality if you don't consider the topology of your space.